So we're going to talk about MPI, which is the message passing interface. Okay, MPI also stands for the name of this ship, apparently, which actually goes offshore and builds windmills. Interestingly. Okay, so we're gonna introduce MPI, tell you about what it is. We're gonna review a little bit of parallel programming concepts, and we're gonna talk about these 6 necessary MPI commands for, you can pretty much do almost anything that you would want to do in MPI, as long as you know these 6 MPI commands. And then we'll look at an example. Okay, so the message passing interface, MPI, is a standard. That's what it is. It's a message passing system designed to function on a wide variety of different parallel computing architecture. The standard has evolved over the years, so it started in the 1990s. In fact, when I just came into the room just before, I was talking to a guy and he was like, "Oh, I learned about that as an undergrad in the 90s," because yeah, that's when it got started. And so it is a standard. It has evolved over the years in order to accommodate advances in hardware and programming practices. And so it's a document. MPI is a document. It's an industry standard. It's at least 200 pages of light reading. If you have insomnia one day, you might consider reading it. It's implemented by a lot of vendors. So there are also open source implementations. And so like Cray, which is now HPE, but they have their own implementation that's on ProLetter. And it is based on MPitch, which is an open source implementation. And basically we use the function library to write our C, C++, or Fortran programs when we're doing HPC. So here's kind of a little bit of a timeline, I guess. So MPI 1 came out in 1994, and that's probably what he was learning. And it just provided sort of your basic point-to-point and collective communications. MPI 2, there were some extensions like dynamic process management, some parallel I/O, and one-sided communications. MPI 3 was not until 2012, but it had a lot of additions, and this is like a 800-page document, if I recall. But it introduced non-blocking collective operations, one-sided communications, and better shared memory programming support, and support for the Fortran 2008 standard. MPI 4, there were some enhancements, but I don't think there's anything very interesting in 4. And then in 5 just got released just this month. I would assume that was at ISC. Yeah, ISC is a big conference that's held in June. And so now there is a standard binary interface, application binary interface to allow interoperability of different implementations. Oh, that's nice. That's going to be really nice. So if we go back here, MPitch and OpenMPI, they tend to not be compatible with one another. If you compile something with one, you can't use the other one because the way they implement it underlying is different. But if they follow the MPI 5 standard, then that won't be the case any longer, and that'll save us a lot of tickets. We get questions about that. Okay, so let's talk. Oh, okay. So we are going to talk about the MPI 4 standard. So first of all, there's new partitioned communications, and this is for like GPUs. Previously, you couldn't exactly communicate directly with a GPU, but now you will be able to partition it into parts that can be processed independently. Persistent collectives, and then fault tolerance, ways to handle failures in their hardware, and then enhancements for hybrid programming. Okay, so I guess there were cool things in the 4.0 standard. Okay, so let's talk about when we're doing a parallel program we have two sort of programming paradigms that we typically operate under. So one of them is called SPMD and the other is MPMD. SPMD stands for single program, multiple data. So if you think about that, that's like we're doing the same operation on many different sets of data. And then the second one is called multiple programs, multiple data. So we're doing different things to different parts of our data. And we can use MPI for either of those. Just wanted to bring that out here where we talk about it a little bit. We're going to go a little bit more into it. So with SPMD, like I said, we're running a single program and it's going to perform the same operation on multiple sets of our data. So if you think of this as like multiple chefs, they're all baking lasagnas, or if we're talking about rendering different frames of a movie, that'd be another example. We're doing the same rendering operations, but our data input is different. Okay, MPMD is we're writing different programs to perform different operations on multiple sets of data. So if we had multiple chefs and they're each preparing different parts of our really fancy 4-course dinner, that would be an MPMD, sort of an algorithm. If we are rendering different parts of the movie frame, like we have one process that's rendering, I don't know what cool movies the kids watch nowadays, but one part is rendering Shrek and the other part is, and another one is rendering Princess Fiona or whatever, right? They're doing different parts of the movie frame. So those require sort of different algorithms for each of those characters. But it's still sort of on the same sorts of multiple sets of data. Okay, and then also, because why not, we can also write a hybrid program where we have some processes performing the same tasks and we have others that are doing different things. Okay, so let's see if we've got, oh, avatar. Okay, avatar. Yeah, that would have been. Okay, so next we're going to talk about the 6 necessary MPI commands. Okay, so these are the 6 commands. And I'm doing this in C or C++ format, but you could, these also exist in Fortran. And if you look at the standard, it'll tell you how to invoke these in Fortran. But it's MPI init, MPI finalize, MPI com size, MPI com rank, MPI send, and MPI receive. And if you know these, you can do almost anything that you would want to do using MPI. It just may not be the most efficient way to do it. Okay, so MPI init, this initiates MPI.
If anyone has not ever used or programmed in C before.
That's probably true, but most people probably have just used like Python or something. Yeah. Yeah, see, when I first started teaching this 20 years ago, before you all were even born, you know, Python wasn't even a thing. But now Python is what everybody uses. And so, yeah, that is a problem. But you can use MPI in Python as well. There are wrappers called MPI for Pi, best one. But I'm afraid that today we are just going to talk about C or Fortran. If you want to talk about Fortran, we'll talk about Fortran too. Okay, so MPI init, that initiates MPI. So what that does is it starts it up. Okay. And so you want to place this function in the body of your code after your variable declarations, but before any MPI commands. And so it just starts up MPI. And if you do any MPI commands before MPI init, their behavior is undefined. So you might get away with it, but you might not. So don't do that. And then MPI finalize shuts down MPI. And so you want to place this near the end of your code after your last MPI command. And it just terminates it, right? It shuts it down. You can't do any MPI functions after that, except if you wanted to re-init or finalize. Okay. Okay, our next ones are about environmental inquiry. So this is the MPI com size and MPI com rank. Okay, so when you start up program, you start it on a certain number of processes. okay? And this is decided before the program starts. And you can start up a program, a parallel program, actually using just about any number of processes, depending on how big your machine is and how many processes it will support. And so what this one does is it tells you how many processes you started up on, okay? And this allows for some flexibility, and that way, like, let's say you want to run it on, 4 processes to test it, and then you want to run it on 4,000 in order to actually run it. Well, you don't have to go back in and edit your code in any way. You can do that without changing anything in your code. Okay, the next one is MPI COM rank. And what this does is it tells you the identity of the current process that is running. Okay, this is probably to kind of make people's brains hurt if they've never really thought of it this way. But basically, every process that is running in MPI has a rank. It just has a number assigned to it. And the number is anywhere from 0 to size -1, okay? And so let me show you a little diagram that I think ought to help make this more clear. Okay, so if I'm running, let's say I want to have 6 processes, okay? I do that using my job script, using Slurm. And I tell Slurm, give me 6 processes, and then I do srun, which is what Slurm uses to launch your job. And I tell it I'm having 6 processes, okay? And so then what happens is, these are actual, let's say these are actual like physical nodes that are on my cluster, okay? Like physical hardware. What MPI will do is it'll say, okay, cool, you have 0 through 5 here. And I'm gonna assign 0 to the first CPU on the first node. I'm gonna assign 1 to the second one, well, the 0th and the first, I guess. I'm gonna assign 2 to just this one. I'm gonna assign 3 to CPU 0 on node 3, 4 to CPU 1 on node 3, and I'm gonna assign 5 to CPU 0 on node 4. Okay, because I told Slurm this is what I wanted. Okay, I set that up ahead of time. Okay, so this is kind of like the world, if you will, of our program. It's what it understands to be reality. Okay, I know that's very anthropomorphized, but hopefully that kind of explains like what's going on here. So what happens is basically MPI, it starts up 6 instances of your program. Each of them are identical, except each of them has a unique rank. Okay, so when I create my program, design it, what I'm going to do is I might have like different tasks for different processes, depending on, first of all, how many there are, right? So that's the size, and then which individual process that is doing it, okay? So from each process's point of view, it starts the program. It has information about who am I and who is everyone else in my world, okay? And that world is called MPI COM world. That is a variable that is just automatically created in MPI, okay? And so then each of these will be executed following the procedures that you have, designed in your code. And if there's anything that depends on the rank or the size, then that's where the execution is going to differ. Okay, does that make sense? Does anybody have any questions about that? Kind of like can blow your mind a little bit.
I questions here, encouraging people to ask in Zoom chat in the Google Doc.
Okay, yes, please ask in the Google Doc. Yes, I see there's some.
There's a question: is rank really prior?
Okay, no. Rank is completely different from priority. Rank is just kind of giving them a name. Yeah, I mean, you can use the fact that the names aren't.
Yeah, GCC.
I'm sorry.
Repeat the question.
Oh, sorry. Okay. Is rank priority? And the answer is no. Rank is not priority. It's just giving each process an individual name. So instead of giving them names like Alice and Fred and things like that, we give them the names 0, 1, 2, 3, 4, 5. And of course, you can use that to your advantage, right? Because you can divide them in half. You can say, okay, anything that's in the lower half, I'm going to do one thing. Anything that's in the higher half, I'm going to do another. You can also do any even numbers are going to do one thing. Any odd numbers are going to do another. And so that's why. But really, 0, 1, 2, 3, 4, 5. That's just their names. Okay. Any other questions?
There's another one on.
Is there one entrance node that we enter through, or are all of the nodes the same? Okay, that's a great question. Aisha, is there one entrance node that we enter through, or are all of the nodes the same? Okay, so the way I would answer that is all of the nodes are basically the same. And it kind of depends on how your batch system is set up. But if you created an interactive job, okay, where you had multiple nodes, there would be one node that you would land on of those nodes. Okay. So in that sense, yeah, there's kind of an entrance node in that. And then if you're running a batch job, if I'm not mistaken, that same node that you would have entered in on during a interactive job is also kind of the node that kind of controls everything within your job. But other than that, really all of the nodes are the same. It just one of them gets chosen to just be the first one in the order. And then Ritesh has a question. Some of the processes sharing the node. Why is that? Okay, that's a great question. Really, the way that most modern systems work, this is kind of like a really old system. Okay, so when I was your age, our systems actually had one CPU per node. Okay, one core, a CPU had one core. And then as I started off in my career, they got to the place where we had 2 cores per CPU in a node. And then our greatest machine that I ever worked on at Oak Ridge, #1 on the top 500 list, Jaguar, it got upgraded to have 4 quad cores per node. Okay, and so in a real computer of today, you're actually going to have a whole bunch of CPUs or cores in each node. So Perlmutter today has 256 cores in a node. Okay, so in reality, in a real today application, unless you specify otherwise, you would, if you wanted to have 6 ranks here, you would just use one node. You know, you would only use 6 of the 256. Okay, 250 of them would just be, you know, hanging out, not doing anything. And there are reasons that you might want to have only one per node. For example, if you know that you're going to use a lot of memory for each of your MPI processes, then you might just want to use 1 per node or 2 per node or something like that, so that you can take up more memory space with each MPI process, because they are independent in memory. So if you have a big data set that you put into like an array or something, then that's going to be reproduced independently for every single process that you have. So if you had a really big data set that you're putting in there, you might need to spread it out more. I hope that made sense, and let me know if there's any other questions. Okay. Okay. Okay, Ritesh, yeah, go ahead and ask.
Yeah, thanks. So one thing that I was like not very sure about is that you mean the node is basically the entire chip, and then inside that node you have multiple cores that's what you mean by CPU 0, CPU 1.
Yes, that's right.
and most of the current generation CPUs will have like 256 or 128 number of cores.
Correct, yes. Yes, thank you. Okay,
If you are putting two CPUs in one node, will not it make congestion? Like you are putting in node 2, you are just putting one CPU, and node 1, you are putting CPU 0 and 1.
yeah, I mean, this was, yes, you could do it that way, and that's probably what you would really do. This was just trying to illustrate the fact that you could map the processes to any of the nodes in the cluster. And you could map them in a bunch of different ways. But typically, yeah, if you were gonna do this in real life, and let's say that you couldn't have more than 2 MPI processes per node, then you would probably, yeah, you would probably just only actually use a total of 3 nodes. And you would just kind of combine what's on node 2 and node 4, or whatever, combine them into, just, compact it, basically. Okay, so let's see if we can go on to message pass. Okay, so we've talked about how to start up and how to stop MPI. We talked about how to figure out what the size of the MPI communicator is and what rank particular process is within that communicator. And so the final thing is we got to actually send some messages, right? That's what the passing part is for. Okay, so the first thing we can use this function called MPI_send. And so what this does is it performs a send. It sends data from one MPI process to another. So if I invoke it I'm process 5 and I invoke it, I'm going to be sending from process 5 to a different process. Okay, so what it's doing here is this is a buffer. This is basically what this is it's where your data is stored, okay? So it could be like an array, it could be actually a single variable, but it's like this is like saying, here's the address where you can find my data that I want to send, okay? This count thing has to do with like how many pieces of data that I'm going to be sending. And then this data type thing tells you what kind of data, okay? So I could be sending integers, I could be sending doubles, I could be sending, floating point, just floats, single precision floats. I could be sending a lot of different types of data. And so this count is like how many items of that particular type of data. So it's not the size of the buffer, it's the number of this particular type of data that we're sending. Okay, and then this is our destination. So this is who we're sending it to. And then this tag thing here, this is like, if I want to make this, make sure that this send is received by a corresponding receive that is unique, then I would put a tag here that would be unique to a match with a corresponding receive. And then this is our communicator. And so this is what we talked about here, our MPI comm world. This is the universe, the world in which we exist and we are sending messages. Okay. So here's an example of it. In this case, I've decided that X is a double. Okay. And it's just a constant. It's not an array in this case. And so this ampersand says the address of where X is stored in my memory. And 1 indicates I'm sending one number. And then MPI double, this is an MPI defined macro basically for double precision sort of data types. And then manager is just, again, I made that up, but a lot of times you might have what we call manager worker algorithms where you have a worker, it's sending its information to the manager that's going to then do something with it and make decisions for how we're going to proceed in our algorithm. I'm just saying that is like using that as the tag. I'm saying me is like my MPI rank. And then MPI comm world, like I said, that is our universe here where this program exists while it runs. Okay. And so then if we have a send, we've got to have a receive, right? So it's pretty much the same. We've got our buffer here, and this is where we're going to receive the data to. This count thing kind of is like the upper bound of like the size of what we're going to be receiving of a particular data type here. And source is like who is sending it to us. And the tag is, again, that unique identifier, because we may have a lot of different sends and receives and we want them to be, to kind of go to the correct place. And then, of course, we've got our communicator, which is MPI ComWorld typically. And then our status, this is the difference here. In if you see in send, we don't have status, we have status here. And so the status is like, how did this go? Did it work? Did we actually successfully receive some data? Okay, so again, so this is supposed to be kind of parallel to this one. So MPI receive, and again, ampersand is telling like what the address is where we want that data to go to. And we're going to receive data of length 1. It's a double, and it comes from somebody, from some source that used itself as its identifying tag. And then we're doing this in our COM world. And then status is like an MPI data type. This MPI status, it's an MPI data type. And so we would just define this variable at the beginning of our code. Okay, and in fact, we will look at a code in a moment. So I just want to bring up the fact that our standard receive function is going to be blocking. So what that means is that it will return, it'll end, only after it actually receives something. So if it doesn't receive anything, it'll just keep sitting there waiting to receive something. And send may or may not block until the message is received, but a lot of times it does block. And it kind of depends on the implementation of it. Because MPI send will block for like really big messages, but often it won't block for really small messages. So we have to be careful about deadlock, because otherwise we could be in trouble. So here, so deadlock can occur if we don't properly order our send and receive operations, because we could have an operation that's just waiting on another one indefinitely. So in order to avoid any deadlocks, we need to be sure that our send receive operations are all properly matched. That's like a pretty common issue when people are developing an MPI code. You could also consider there are non-blocking communication functions, but we're not going to really talk about those today. Or you could change the program structure in order to avoid any kind of circular dependency. So here's our example of a circular dependency of deadlocking. So we'll always deadlock. Okay, so this is a real MPI program. You could copy and paste it. You may have to fix, I guess, the quotation marks in it. But other than that, you could copy paste this thing into a doc, like a file on Perlmutter and compile it and run it, and you would see that it would deadlock. So this is a real MPI program. So we need pound include MPI.h. That is our MPI header library, and what that does is it defines all of these things here that are MPI unique to MPI. And then this one here has to do with standard I/O, so that's so that we can actually print things. So I have my main body of my code is main. I've just defined some variables that I'm going to need, and then I initialize MPI. I figure out what is the size of my MPI communicator. So how many MPI processes are there? And what is my individual rank when I'm running this program as an individual? So honestly, this program exists to demonstrate deadlock, but really what it's trying to do is exchange data between neighboring processes. So 0 and 1 are going to exchange their ranks, which is an integer number. They're gonna exchange their ranks, 0 and 1. 2 and 3 are gonna exchange ranks, 4 and 5, etc. Depending on how many processes I have, but I need an even number in order to make this work. Okay, so if I am an odd number, rank, then I'm gonna send to my neighbor that's below me, right? So if I'm 1, I'm gonna send to 0. And then if I'm 0, because I'm not odd, I'm 0, I'm gonna send to 1, because that's gonna be 0 plus 1. Okay, so then what's gonna happen is I'm gonna wait to receive the information from my neighbor. And then after I receive that information from my neighbor, then I'm gonna send my information out. Okay, so can people see why this would deadlock? Any thoughts? Some people online. Yes, both are waiting for a response from the other one first, right? So if you think about it, you're processor 0, I'm processor 1, okay? We both go into this and we know we're gonna be exchanging information. I'm out here with my hands out waiting for your information. You're out there with your hands out waiting for my information. And because MPI receive always blocks, then we're just gonna be sitting here like forever until the end of time, or until the time the time that Slurm allows you to run your job, or until the machine gets decommissioned, whichever comes first. We will just be sitting here forever with our hands out, not doing anything, waiting for the other person to send. Okay, so allegedly after we sent, we were gonna make a message about what we received and sent, and then we were gonna MPI finalize, and then we were gonna quit.
So
Okay.
should the receive line be below the send line?
Well, that's my next idea, yes. So this program, actually, if you ran it on Perlmutter, it would work. You would not have a problem with it. Because send doesn't always block, but sometimes it does, depending on the size of what you're sending. I'm sending a single thing, it's no big deal. It's not gonna block. It's kind of like if you think about, if somebody sent you a letter, like the letter carrier is just gonna go put it in your box, and then you can receive it when you receive it, right? On the other hand, if somebody sends you, some giant gold bars or something, okay, they're not just gonna leave it on your doorstep and hope that you receive it, right? They're gonna knock on your door. They're gonna make you sign on the dotted line to say that you have received it, right? So it's a similar idea here. So if I send a single integer to somebody, who cares? If it got lost, I'll send it again. If I'm sending you giant gold bars, so I'm sending you, a really big message, I'm not just gonna send it. What actually usually happens when it is a blocking send is a little message that comes out and says, hey, I'm gonna send you a message. Are you ready? Right? And then if you say, yeah, I'm ready, then they'll send you the big message. Otherwise, it'll wait a while, and then it'll say, hey, I'm gonna send you this message. Are you ready? Right? And it'll just keep pulling you until you're ready. Okay, so if these were big messages that we were sending, then we would just have these couriers all the time just saying, hey, are you ready? And then you would send your courier to me and say, hey, are you ready? And neither of us would actually be ready because we're still trying to send, right? So like I said, this will sometimes deadlock, but with just a single integer that I'm sending, it's not gonna deadlock. Okay, so here's the way to make it work all the time. So basically what we're gonna do is we're gonna say, if I am an even numbered process rank, then I'm gonna send and then I'll receive. And if you're an odd number, then you will receive first and then you will send. Okay, and so with the way this works, this balance, then this will always work because there won't be any potential for any deadlocks. Okay, so this is another one that you could copy paste out of here, run on Perlmutter, and you would see that it would work. Okay, any questions about our examples here? I see some in chat. Maybe.
Question about, do you have to do MPI receive, or is there any way for it to automatically be received?
You always need some kind of a receive to match with your send. Yeah. Okay, so we already kind of went over this, but the always deadlocking example is just logically incorrect. It is caused by blocking MPI receives, and they're all waiting for a corresponding MPI send to begin, which would never happen. Okay, the sometimes deadlocking is logically correct. Deadlock could be caused if your MPI sends are competing for buffer space, so it's unsafe because it depends on system resources. And so instead you want to do like what we said, reorder the sends and receives, or you could use non-blocking sends and receives or other advanced functionality. And so you can see the MPI standard for more details about that, but that's how it would go. Okay.
I had a question about the,
Uh-huh.
in the code, there's several uninitialized integers that you pass in, pass the address to some of these functions. And I guess I got a little bit lost as to, I guess I don't understand necessarily even what's happening when you're passing these, because me doesn't seem to actually have any value. I assume when you pass it to com rank, it will take on some value, but
That's
I
right.
guess I don't see how there's like multiple processes that are even being necessarily spawned here. So that's where I got a little snagged on what's going on.
Sure, okay. Yeah, thank you for that question. That is a really great question. I appreciate you asking it. Okay, so I created these variables up here, right? And so what I did was basically I told the program, okay, give me like a piece of memory that is integer sized that is called me. Basically, that like if I call the variable me, it understands it means whatever's in that location right there. Okay, it's kind of like the address for that. So then when I come down here and I'm doing com rank, then what I'm actually providing it with is the address for me. So it doesn't matter what was stored in that space before. What's going to happen is MPI com rank is going to take the information of what rank that it is running on, and it's going to just like put that into that address space where me is located. Okay, so it doesn't matter that I didn't really initialize me. Like I wouldn't want to like get the information out of me until it had been set by something like MPI com rank. Okay, and then yeah, go ahead.
So I guess maybe I'm still just much more comfortable with serial execution, because in my mind, me should only have one value in this code, which it's going to take on some rank. So then where is this me -1 that we're sending to? Like, I guess that's where are we even saying, here's how many MPI processes that we are initializing?
Right, so that happens in MPI init. And really, me does have one value on each MPI rank, right? It has a unique value for that MPI rank. So you can think of this like if the size, let's say, is 4, okay, then we have 4 copies of the code running, okay? And when we yeah, go ahead.
Where is that 4? Is that in argc, or is that, is that like one of?
It's not in this code.
I mean?
Yeah, so what happens is the way that we would make this run with 4 MPI processes is we would tell Slurm, hey, I want to run this code with 4 MPI processes. And, you know, so it's under S run, then there's a minus lowercase n, and we put a 4. Okay, so that.
And
so-
that's gonna get passed to your executable.
That's gonna get passed, right, that's gonna get passed through MPI init. So MPI init has some magic that happens behind the scenes that you can look at the source, you can read it and, you know, have another insomnia cure for you there. But what it does behind the scenes is it just decides like, okay, you're process 0, you are process 1, you are process 2, you are process 3, and here's how you are all connected.
Okay,
Okay, so we have 4 identical executables running, but there's just only one like kind of difference between them, and that is that they each have a rank that is different than the other. But other than that, they're all running our same program.
so if I distribute to say 4 CPUs, will each CPU actually then run this MPI init, or is that only happening on one CPU and then instruct like further instructions, or does each process get a complete set of the executable?
Each process has a complete set of the executable. And so,
Okay.
so they proceed through here, they get to MPI init, and that's where magic happens that I don't really know exactly how it happens, but it's not actually magic. I mean, you can read the source code and find out. But at that point, they become aware of the other MPI processes that exist, and they become aware of their own identity.
Awesome. Thank you so much.
Yeah, very welcome. And thank you for asking the question that maybe other people weren't brave enough to ask.
Absolutely.
Okay, so hopefully that makes sense, and then we can talk about computing pi. Okay, y'all may not know this who are online, but I'm wearing my super cool pi sweater today because I love pi. And so we're going to compute pi in parallel because it's easy and it's fun. So we'll talk about this, and then what is our schedule like? I think we're running late. I'm sure we're running late.
We're a little bit behind take your time.
Okay,
Can adjust.
Yeah, we can adjust. Take your
we'll
time.
adjust the schedule. Okay, good.
Take your time.
Okay, so let's say we want to compute pi. So one method is the method of darts. Okay, now in real life, don't ever use the method of darts to compute pi. The reason we're using the method of darts is because it's really easy to understand and to parallelize. Okay, but don't use it in real life because it's not an efficient way to compute pi. Okay, anyway, the point of the method of darts is that the ratio of the area of a square to the area of a circle that is inscribed inside of that square is proportional to pi. So we can use that knowledge to then compute pi. So method of darts, we could do this at home actually. So imagine that you have a dartboard and its radius is r and it's inscribed in a square. And if we do the math here, the area of the circle is, of course, pi r squared, right? The area of the square is the quantity 2r squared, so that's 4r squared. And then so that if we take that ratio, the area of the circle divided by the area of the square, we get pi r squared divided by 4r squared. R squared cancel out, and we have pi over 4. Okay, so that's how we're gonna do it. So you're like, okay, that's exciting, but like, how do we actually do this? How do we find the areas? Well, let's say we were doing this at home and we just threw darts completely randomly at the dartboard. So we're not trying to hit the center or anything. We're just throwing darts in that general direction. If we counted the number of darts that landed inside of the circle versus the total number of darts that we threw that landed in the square, the ratio of those numbers would give us an approximation to the ratio of the areas, right? Because like by random chance, there's random chance that we're gonna hit any given point. And so the quality of our approximation increases with the number of darts thrown. And unfortunately for us, with this algorithm, actually, the quality of our approximation increases by a very slow factor. So we have to actually throw 10 times more darts in order to get one extra decimal place of accuracy. Okay, so like I said, it's actually not a good way to compute pi, but it's easy and we understand it. Okay, so I am like the world's largest nerd, as you might have figured out by now. And so I actually made myself a method of darts cake a number of years ago, because actually I like cake better than I like pie, but don't tell anyone. And so I used some sprinkles to try to illustrate the darts. And so hopefully, I don't think it probably worked with this cake, but ideally the number of sprinkles in the circle versus the number of total sprinkles would be pi over 4. And so then therefore pi would be 4 times the number of darts inside of the circle divided by the total number of darts thrown. Okay. So, okay, that's great, but like, how do we actually simulate this on a computer, right? We've seen the dartboard version, we've seen the cake version, but what about the computer version? Well, it's actually fairly straightforward. So we just decide on length R. I like 1 personally, 1 is my favorite. And then we're gonna generate pairs of random numbers such that those numbers X and Y are, less than or equal to, less than negative, let me start that one more time. Greater than negative R and less than R. And so then if they lie within the circle, that pair of random numbers, then we're going to add 1 to the tally for things that landed within our circle. And then when we're done doing that, then we're going to find the ratio of those. Okay, so does anybody have any questions about the method of darts itself, like the principle behind it? Kind of makes sense? Okay. So I wrote the code for how to do it. So here's the code. And so I'll explain how this code works. So this is our random number generator, okay? That we will see that in a minute. But we're gonna do 1,000,000 darts. Okay. And so then we're setting some variables here. So the number of darts in our circle, we're going to call that 0. Oh, and long is basically integers, but extended to really big integer numbers. And so we're going to have pi, x, and y. We're going to have the radius. Like I said, I like 1. 1's a good radius. And then radius squared is just r times r. And then we're going to go through this loop, and we're going to do this 1,000,000 times. We're going to calculate x and y, and we're going to see if they are less than or equal to r squared. If they are, we're going to add 1 to our tally. How many are inside of the circle? If not, we won't add that. And then at the end, we're going to calculate pi. So that's going to be 4 times the number that were inside of the circle divided by the number of trials that we did. And then we're going to print it out and we're going to leave. Okay, pretty straightforward. Do I see a question? Oh, why I plus plus instead of plus plus I? I don't know. So I plus plus, okay, I plus plus, what it does is it is a post addition, right? I think if you do plus plus I, you might only do 999,999, but you would have to check. Okay, now here's our random number generator. Okay, this is actually a pretty terrible random number generator. So if you ever need a random number generator, don't use this. But it is easy to understand, and so that's why we're using it. So this is what's called a linear congruential random number generator. And what it does is it basically, it utilizes the mutual primality of these three numbers, I believe. They're all mutually prime to one another. And it uses that to produce a very long sequence of numbers that appears to be random, but actually isn't. Okay, and so the way it does that is it creates the next number by multiplying the last number by the multiplier and adding the addend to it, and then taking the modulus of that, so the remainder of it divided by p mod. That's how it does it. And then it normalizes it to a number between 0 and 1 in this line right here. Random next divided by p. Okay, and by the way, the reason I have these double in parentheses here is these are integers, well, they're longs, but those are basically integers. And if you divide this without putting these doubles here, you would actually get 0. Because integer division is just taking it just doesn't keep anything beyond the decimal point. So that's why we have to do it that way. And so this is called casting, I think, typecasting. Anyway. All right, if you like Fortran, we also have it in Fortran. I won't go over it too much, but this is the random number generator in Fortran. And then this is the program in Fortran. Okay. So what we're going to do now is we're going to think about how to parallelize this. So what tasks are independent of each other? What tasks have to be performed sequentially? And we're going to use PCAM to design our parallel algorithm. So let's think about this. So what tasks are independent of each other?
Generating random numbers.
Generating random numbers, okay, hopefully that's true. But let's think about it in terms of darts. Like if we're doing the dart algorithm where we're actually literally throwing darts. Throwing a dart is independent, right? Yeah, if I throw a dart and you throw a dart, right? It doesn't matter if I throw one first or you throw one first, right? We're still gonna be, it's in parallel thing. We don't have to, there's no particular order that's requiring. Yes, okay, good. Each dart throw. Squaring numbers, the random generator. Each dart throw, good. Checking if they're in the circle. Okay, yes, sampling random numbers and checking if they're in the circle. But you need to create your random numbers. You need to throw your dart before you can check if it's in the circle, right? So that is sequential. And then also we need to throw all of our darts before we try to calculate pi, right? We can't calculate pi first and then throw the darts. So those are just things to think about when we are doing our algorithm design. Okay, so the first step is partitioning, right? So partition, if you recall, is to decompose the problem into fine-grained tasks to maximize the potential parallelism. So I'm going to assert that the finest grained task is the throw of one dart. Okay, I mean, you could say that the finest grained task is the creation of, the generation of random number. But because we have such a fiddly random number generator, I'm going to say it's not. I'm going to go with the throw of a dart. So like we were discussing before, each throw is independent of all others. And if we had a huge computer, we could actually assign one throw to each processor, right? Unfortunately, I forgot to reserve the million processor computer, so it may not work for us today. So let's talk about communication. So what's going to happen if we're all throwing darts and figuring out whether the dart is in the circle or not? Then what do we need to do? We need to communicate that information back to some centralized location, right? So I mentioned this before, manager-worker algorithms are very typical, very common. And so this is an example of a manager-worker sort of an algorithm where all the workers do some stuff and then they report back to the manager about what they did. And so if we had our million processor machine, each of them, you could say each processor throws one dart and sends it to the manager. Okay, but let's think about this. Now we're thinking practically, we're going to think about agglomeration, combining into coarser grained tasks to reduce the communication requirements or other costs. So to get a good value of pi, we have to use millions of darts. Like I said, we don't have millions of processors available, so we can't really do it that way. Furthermore, if you think about the communication between the manager and millions of worker processes, that could be very expensive. And in fact, if we had a million processes and each of them did one throw, it would actually be way more expensive for them to send their information to the manager than the cost of them throwing. So our solution here is going to be to divide up the number of dart throws evenly between a much smaller number of processes and give each of them a share of the work to do. So finally, we're talking about mapping. So we mentioned how this is a manager worker type of an algorithm. So we're going to assign the role of manager to processor number 0. And the reason we're doing that is because in our MPI comp world, there is always a 0. But if you decided, oh, I'm going to assign it to processor 7, well, maybe you don't even have a 7, right? So that's why, by convention, we use processor 0 to be the boss. Okay, and so process 0 is going to receive the tallies from all the other ones, and they're going to compute the final value of pi. And so everyone, including the manager, is going to perform an equal share of dart throws because this manager just has to do one thing at the end, right? So it's not like it doesn't have a lot of extra work to do. So it can perform its own share of the dart throws. That seems fair. Okay, any questions about PCAM and how we've kind of figured out our algorithm here? No, okay. All right, so this is your assignment. So we already asked you to clone the repository. And then you want to copy out darts.c and lcgenerator.h or darts.f90 from the right directory. And then we're going to parallelize it using the 6 basic MPI commands. And we're going to rename it. We're going to call it darts-MPI. Okay. Any questions about